Along the Dutch coast, sea level has been rising by roughly 2 to 3 millimeters per year, and accelerating. In some parts of the country, the ground you'd be standing on sits nearly 7 meters below that rising water. Amsterdam itself sits 2 meters under it. And every single day, without exception, that difference has to be managed. Otherwise, there will be flooding. 26% of the entire Netherlands lies below sea level. Around 60% of the country would be vulnerable to flooding without its engineered water defenses. And still, 18 million people live here, permanently, right next to a sea that's already higher than their homes. No single wall makes that possible. It takes an entire system. Dozens of structures linked together so precisely that nothing overlaps. Nothing is left uncovered. So how does an entire country stay dry below a sea that keeps climbing? And what happens the moment one piece of that system fails? Join Breakthrough Engineering as we uncover the system that keeps the Netherlands alive.
One of the deepest points sits right where Schiphol Airport now stands, built on the bottom of a drained lake, 4 meters below sea level. Its name literally means ship hole, after the vessels that used to sink there. Millions of passengers land there every year without knowing they're touching down underwater. So what does it actually take to keep water at that level down permanently, reliably, crisis-proof, no matter what the sea throws at it? It took a disaster to make this possible. On a January night in 1953, a storm and a spring tide struck the Dutch coast together, killing more than 1,800 people. The worst flood in decades. Weeks later, the government decided never again, whatever it cost. Instead of raising dikes bay by bay, the new plan was to close off entire river mouths and shorten the coastline itself. That became the Delta Works, a network of storm barriers, dams, and locks across the Southwest Delta, built from the 1950s until 1997. Not every sea arm got sealed the same way. The Oosterscheldekering was meant to be a solid wall, until engineers realized it would kill the tidal ecosystem behind it. It became a movable storm barrier instead, open on calm days and sealed only for a surge rare enough to hit once every 4,000 years. Further north, the Afsluitdijk took the opposite approach. A 32-kilometer dam, built in the late 1920s, sealed the Zuiderzee shut completely, turning it into the freshwater IJsselmeer, drained by gravity through tidal sluice gates. Though rising seas are now shrinking that gravity window, forcing engineers to add pumps. Together, these projects earned recognition as one of the 7 wonders of the modern world. Rotterdam's port needed something none of the sealed-off river mouths could offer: a connection to the North Sea that stays open almost all the time. A fixed dam would have shut down one of Europe's busiest shipping routes, so they built 2 movable steel gates, each about 210 meters long, mounted on steel truss arms that swing out from both riverbanks. Together, they close a 360-meter-wide waterway. Each of those 2 arms weighs around 6,800 tons. In calm weather, both gates sit parked in dry docks on land. When a computer system flags a dangerous water level forecast, the port closes to traffic. Both gates swing into the river, flood themselves with water, and sink onto a sill on the riverbed under their own weight. Once the storm passes, the water is pumped back out, the gates float free, and they swing back to shore. No person confirms that closing call. It's made entirely by a computer, because engineers decided the temptation to wait just 1 more hour was too dangerous to leave in human hands. Since the barrier was finished, it is only closed for a real storm twice, in 2007 and in 2023. That second closure came on December 21, 2023, during Storm Pia, when water levels in Rotterdam were forecast to reach 3 meters above normal, enough to trigger the IJsselmeerkering's automatic threshold. It wasn't alone. That same night, all 6 of the country's major storm surge barriers closed at once, sealing off the entire Dutch coast simultaneously for the first time in history. Dikes solve one problem, keeping the sea and rivers out, but not what happens to the rain and groundwater already trapped inside them. Many polders sit lower than the canals, rivers, or the North Sea around them, so water inside has to be lifted, not drained by gravity. The system works in stages. Small ditches collect rain and groundwater, feed it into larger polder canals, and a pumping station lifts it into a higher regional canal system called the bosom, from where it finally reaches a river, lake, or the sea. Windmills used to do this work. Steam engines, diesel motors, and now electric pumps took over, but the basic principle never changed. The Vuda pumping station in Friesland, opened in 1920, is still the largest operational steam-powered pumping station in the world. Its 8 pumps can move about 4,000 cubic meters of water a minute, roughly 66,000 liters every second, and it's kept in reserve today for exceptionally high water levels. These pumps can't just run at full power all the time either. Pump too little, and streets and basements flood. Pump too much, and peat soil dries out, oxidizes, and sinks even further. Water levels have to be managed precisely, not simply pushed as low as possible. Not every defense pushes water away. One of the country's boldest ideas was to give rivers more room instead. It moved dikes further back from riverbanks, dug new flood channels and side arms, lowered floodplains, and also turned entire polders into deliberate flood storage. It was carried out at more than 30 locations along the Rhine's branches, the Meuse, the Wall, and the IJssel, at a cost above €2 billion. Near Nijmegen, they didn't just move a dike back. Engineers cut an entirely new channel through the floodplain, splitting the wall into 2 routes and turning the strip between them into a brand new island for the city. The logic? A wider river channel spreads the flow, lowers the peak water level, and takes the load off the dikes. Large stretches of the Dutch North Sea coast have no concrete wall at all. The defense is sand. Dunes that aren't rigid barriers, but reserves designed to lose material and survive. During a storm, waves are allowed to strip sand from the dune, which settles just offshore and helps break the next wave's energy before it reaches land. Since the 1990s, the Netherlands has kept its coastline alive through constant sand nourishment. The boldest version is the sand motor. In 2011, engineers dumped 21.5 million cubic meters of sand, about 8,600 Olympic pools worth, into a single peninsula, then stepped back. Waves, tides, and currents have been spreading it along the surrounding coastline, widening beaches for miles, with no further construction needed. A concrete wall has to withstand every wave. A dune only has to survive by giving part of itself away. None of this, the barriers, the pumps, the shifting dunes, stays alive on its own. Someone has to inspect every dike, maintain every pump, and adjust water levels every single day, forever. That job belongs to the Waterschappen, 21 regional water boards, some dating back to the 12th century, among the oldest democratic institutions in Europe. People here don't just vote for their city, they vote for water too, keeping maintenance funded no matter which party runs the country. It might be the quietest genius move in the entire system. The most important flood defense in the Netherlands isn't concrete or steel. It's an institution that has made sure for 8 centuries that nothing in this system gets neglected, which is exactly why coastal cities around the world, from New Orleans to Jakarta, now turn to the Netherlands for advice on how to manage water and keep their communities safe. If you want to keep exploring the world's greatest feats of engineering, join Breakthrough Engineering for the next one.